Okay, in this video we're going to look at yet another alkene addition reaction. In this case we're going to look at hydrogenation. In hydrogenation we're going to add an H2 to our carbon-carbon double bond. This process requires a catalyst, and it's very common to use a metal catalyst. And the reaction itself is fairly simple. Basically we're just converting the alkene into the corresponding alkane. Without the presence of a catalyst, the addition of H2 to the double bond is much too slow due to a very high activation energy. But as we've learned previously, a catalyst speeds up a reaction by changing the mechanism, and we can see in this schematic that we've changed the mechanism because it went from a one-step mechanism to, in this case, a three-step mechanism, and in the process we lowered the activation energy. So by lowering the activation energy, the catalyst speeds up the reaction, right? But it does not change the reactants or the products. Now in previous videos we've talked about syn and anti-addition, and that's relevant to catalytic hydrogenation as well. And so we only see syn addition with hydrogenation. And so both hydrogens are either added from the top or from the bottom. And so, if the hydrogens were added on the bottom, they'd both be on dashes, so these groups get pushed to wedges. Or if the hydrogens added from the top, they'd be on wedges, and so these groups get pushed to dashes. Now we have to be careful. We don't always get a pair of enantiomers. In the case of a symmetric alkene, then the compound that's produced is actually meso, right? And so whether the hydrogens add on dashes and push these methyls to wedges, or if the hydrogens add from the top and push the methyls down, right, these are in fact the same compound because we have this plane of symmetry. So this schematic of what catalytic hydrogenation looks like explains why we only see syn addition. So we have our metal surface here that has hydrogen atoms attached to it. The alkene comes down and places itself on the metal surface, and so because the hydrogens are coming from the same side, we only get the syn addition. So this slide is just a note on nomenclature and two terms that we use when we talk about catalysts. Now these apply to all catalysts. They're not specific to hydrogenation. And actually, when I made this slide, I had these backwards. A heterogeneous catalyst does not dissolve in the reaction medium. And so typically when we have metals like platinum or palladium, they are heterogeneous catalysts. Another way to think about heterogeneous catalysts is they have a different phase than our reactants and our products. Right? Very often our reactants and products are in solution. The platinum or palladium metal is a solid, and so we have a heterogeneous catalyst. When the catalyst does dissolve in the reaction medium, now they're all essentially in the same phase, and so if they're in the same phase, then they're called homogeneous catalysts. And so an example of a homogeneous catalyst that we use in catalytic hydrogenation is Wilkinson's catalyst. And here's a picture of what Wilkinson's catalyst looks like. Now, one thing that I'm not going to go into too much detail on is asymmetric hydrogenation, but the book mentions it, and so I thought I would at least have one slide on it. So generally we get a mixture of enantiomers, but if we wanted to synthesize only one enantiomer, that process would be called asymmetric hydrogenation. And one way to do that is, rather than using a symmetric Wilkinson catalyst, if I actually make the catalyst chiral, then research has shown that we can get a product where we select only one of the enantiomers as the major product. Okay, so we want to predict the products of the following reaction, and based on my reagents, this is an example of catalytic hydrogenation. And so we're going to add a hydrogen here and here. Now we also need to be aware of the stereochemical factors, and so when we add the hydrogen here, it's already got a hydrogen, so we'll end up with two hydrogens, so this carbon will not be chiral, but this carbon is going to end up with the hydrogen that we add, a methyl, a propyl, and an isopropyl, so this carbon will be chiral, and so we're going to get both enantiomers. We'll get the enantiomer produced when we add the hydrogens from the top and when we add the hydrogens from the bottom. Now I could represent that by changing either the isopropyl or the methyl group. I don't think it matters. I'm going to choose to change the position of the methyl group. And so we'll get, if the hydrogens are adding from the top, then that would push the methyl to the bottom. But then we'll also get the stereoisomer, where if the hydrogens are adding from the bottom, then we'll push that methyl to a wedge. Okay, so one more example. We want to predict the products, and again, this is an example of catalytic hydrogenation. And so in this case, both carbons, when we add these hydrogens, are going to end up being chiral. So we're going to have the hydrogen that we add, the methyl, the ethyl, and then they're going to have a secondary butyl group. But let's take a look and see what these products are. And so first, let's add it as if the hydrogens were coming in from the bottom. And so I'm going to represent that by pushing the methyls to wedges. All right, and then we can also have the product where the hydrogens are coming in from the top, and so then that would push the methyls to be on dashes. And so at first glance, it looks like we get these two different enantiomers. However, bear in mind, right, we have this plane of symmetry in both of these molecules. So in fact, this molecule is meso, and so, right, if I just flip this one over, I get this one. And so in this case, right, we really only get one product. And so it would be incorrect to draw both products because this compound is meso. I only get a single product. And so we have to be careful. When we have symmetric alkenes, then the product that's produced may be meso. And so, in fact, we don't get two different stereoisomers. We just get the one product.